Sir, start on this.
Good morning, everybody. Good morning, all the students, for the second day classwork of geotechnical engineering. Yesterday, we had complete discussion on the fundamental concepts of geotechnical engineering and also deriving various relations of the basic definitions, and also we have seen few solved problems. Now let us continue by solving some more problems and afterwards get previous questions and then switch over to the next chapter. Already we have seen discussed several questions in the last class. All the questions are related to the basic terminology and basic relations of the various properties of the soil. Okay, let us go for another problem. A fully saturated soil sample has water content 10%. Okay, let us see the some more problems on in general. A fully saturated soil sample there's something wrong in system. Please wait for a minute. Okay, let us see the next problem, numerical problem. A fully saturated soil sample has water content of 24%, W, small w 24%, and bulk unit weight of 19.6 kilonewton per meter cubed. Gamma equal to 19.6 kilonewton per meter cube. If the degree of saturation is reduced to 80%, originally it is fully saturated. Fully saturated means degree of saturation equal to 100. Originally degree of saturation 100% and water content 24%. Initial unit weight gamma 1 is 19.6 kilonewton per meter cube. And afterwards the degree of saturation is reduced to 80%. So that is S2 will be equal to 80%. For sample 1, S1, W1, gamma 1 are the parameters, and for the same sample, if the degree of saturation reduced to 80%, S2 equal to 80 without changing in the void ratio. So void ratio means the entire spaces are constant. There is no change in void ratio. That means when the water content reduced from fully saturated to 80%, these spaces will be occupied by the air, and ultimately there is no change in the void ratio. The bulk density of soil sample is. So in case 1 and case 2, case 1, degree of saturation S1, W1, gamma 1. In case 2, S2 equal to 80% and gamma 2 is the appropriate density. And basing on this, the unit weight is always the same. Gamma D will be equal to gamma by 1 plus W. Accordingly, for the first sample, we can obtain dry unit weight equal to 18.51 kilonewton per meter cube. And what is S1? You know the basic relation S is equal to WG by 1 plus E. S is equal to WG by E. So basing on this, you can find out by substituting various parameters. Sorry, it is not S1, it is gamma, because S is equal to 1 in the first case. When S is equal to 1 in the first case, gamma equal to G gamma W by 1 plus 0.42G. So basing on this, you will get void ratio 0.612. Once void ratio is known, by using the equation gamma, bulk unit weight of the soil, G plus Se by 1 plus E into gamma W, you can have the ratio of the densities, gamma 2 by gamma 1 equal to G plus Se by 1 plus E. You know 1 plus E is constant because void ratio is constant. So 1 plus E is constant, and ultimately G plus S2E by G plus S1E, and substitute the various values, you will get the density for the second situation of the soil sample. So in this particular case, originally such soil is completely saturated 100%, water content 24%, unit weight 19.6. These are the parameters, and void ratio remains the same in both the samples. Whereas in the case of second one, degree of saturation reduced to 80%, and gamma 2. Similarly, W2 is also not known, and accordingly we got gamma D value, and basing on the gamma D, by substituting in bulk unit weight of soil formula, the ratio of the two, gamma 2 by gamma 1, will be equal to this formula, and accordingly substitute and get the appropriate values. Excuse me, 1 minute please. Babu? Highlight out legend. Highlighter. Not highlighted.
I think the water version 2007 sir.
Okay, right.
Pen. In the 2016 highlighted.
Okay, chalo. Okay, let's go to the next problem. A fully saturated soil sample has water content of 27%, W, small w 27%, bulk unit weight of 19.2 kilonewton per meter cube, gamma 19.2. The specific gravity of soil solids is. And in the question it is clearly given that fully saturated soil sample. Fully saturated soil sample means S is equal to 1 or 100%. So S equal to 100, W equal to 27, gamma equal to 19.2. These three parameters are given. And ultimately we need to find out the specific gravity. And you know the specific gravity related formula, S is equal to Wg by E, and also gamma D equal to G gamma W by 1 plus E. So by using these two formulas, we can get the unknown parameter. So for in the gamma D formula, G gamma W by 1 plus E, first find out gamma D based on the water content and also bulk unit weight of the soil. So first obtain the gamma D value and then find out void ratio by using S is equal to Wg by E. Here S is equal to 1 because it is fully saturated. So E will be equal to W into G. W is 27%, so 0.27 into G. So E value is known and finally substitute in the formula gamma D and all the other parameters are known except G value and obtain the G value from this particular question. The next one, an embankment of earth fill is to be constructed at a void ratio 0.68 from 1000 meter cubed of borrow pit having a void ratio of 1.1. The quantity of earth fill. Already I discussed in the last class, you know, the generalized relation between the volume of the soil and also the void ratio V1 by V2 equal to 1 plus E1 by 1 plus E2. Substitute the three given parameters and get the fourth parameter, fourth unknown parameter. So these are the types of questions normally encountered in the first chapter. Of course, this problem is also same. Anyway, the material is going to provide for all the students. So next question, a soil sample with porosity 36% has a degree of saturation 50%. Porosity N equal to 36, degree of saturation S equal to 50%. If the specific gravity of the soil solids is 2.7, G equal to 2.7, then the dry unit weight, gamma D, bulk unit weight, gamma, saturated unit, gamma saturated, submerged unit weight, 1 plus E. So in this problem, G is known, gamma W is known, E is not known. But indirectly, in place of E, the porosity is given. Porosity equal to 36%. So once the porosity is known, find out the void ratio. E is equal to N by 1 minus N and accordingly E equal to 0.56. Substitute the same value in gamma T. So the dry unit weight is obtained as 17.31. And let us see other three different units, densities. Another one is bulk unit weight gamma. If you want to know the gamma, you know the relation between the dry density and also bulk density, water content. So if you know the water content, you can use this particular formula. So for obtaining the water content, the formula is known S is equal to Wg by E. So this is the formula. In this formula, substitute all the parameters and get the corresponding water content. Once water content is known, and you can find out the bulk unit weight of the soil. Saturated unit weight gamma sat this is the generalized formula G plus E by 1 plus E into gamma W. Substitute the values and obtain the saturated unit weight of the soil. And submerged unit weight. Already you know the relation gamma dash equal to gamma sat minus gamma W, that is 20.9 minus 10, 10.9. So like that we can find out the various associated densities in a given sample of soil. So these are the sample questions covering almost all the relations. Now let us go for the previous gate questions that appeared in several examinations. This is the question appeared in very recent examination, GATE 2020. Yes, it is for 2 marks. A sample of 500 grams dry sand. So what is the associated symbol WS, dry sand? We can use W suffix D or otherwise W suffix S, that means weight of solids. Weight of solids or weight of dry soil both are same, that is equal to 500 grams. When poured into 2-liter capacity cylinder, which is partially filled with water, displaces 188 cubic meter of water. What is going to happen here? It is taken 2 liters capacity of cylinder, which is partly filled with the water, and by pouring the soil, the water displaces 188 cubic centimeter cubed of water. So that means this is the volume displaced because of the pouring of sand into the cylinder. So that means what is the volume of the sand? Volume of the sand is equal to volume of the water displaced. So that's why volume of the sand is 188. Volume of the sand is the same as volume of the water displaced because of the pouring of sand into the cylinder. So the weight of the dry weight of the soil is known, then volume of the soil is known, then density of water. What is the density of water? 1 gram per centimeter cube. Because everything is in grams and centimeter, let us use in grams and centimeter cube only. And the density of sand, gamma S, equal to, gamma S means soil solids, Ws by Vs. That means weight of the solids divided by the volume of the solids. Already you know weight of the solids and also volume of the solids. Basing on that, gamma S equal to 2.66 grams per centimeter cubed. The question is specific gravity of the sand. What is the basic definition of specific gravity? Specific gravity is the ratio of the unit weight of the soil solids to the unit weight of water. Unit weight of soil solids is 2.66 gram per cm cube, whereas gamma W is equal to 1. So specific gravity equal to 2.66. It is very fundamental definition. Basing on the fundamental definition, this question is posed. So here dry soil sample is given. Volume of the dry soil sample also given. Basing on that, you got gamma S value, dry density of the sand, and accordingly specific gravity of the sand. It's a very recent question appeared in GATE examination. And one more question appeared in GATE examination is second one. A soil has dry unit weight of 15.5 kilonewton per metric cube. Dry unit weight. Dry unit weight of soil. Dry unit weight of soil 15.5 kilonewton per metric cube. Specific gravity 2.65. G equal to 2.65. And degree of saturation 72%. S equal to 72. Considering the unit weight of water 10 kilonewton per meter cube, the water content of the soil sample is. The question is, what is W? You know, when dry unit weight of the soil gamma D is given, when dry unit weight of soil gamma D is given, and specific gravity is also associated, then the associated formula is gamma D equal to G gamma W by 1 plus E. So in this entire formula, everything is known except E, void ratio. Find out the void ratio. But our question is, what is the water content of the soil? And you know the other relation between void ratio, W, G and S. S is equal to W, G by E. S is given 0.72. W is the unknown parameter to be found. G given, E just found. So by substituting all these values, the water content in the soil is 19.28%. It's a very simple formula required for solving this problem. It's also a very recent GATE examination question. Third one, a soil has specific gravity of its solids equal to specific gravity of soil solids is 2.65. So G is equal to 2.65. The mass density of water is 1000 kg per meter cube. It's a simply density of the water 1000 kg per meter cube. Considering zero air voids, zero air voids means Na is equal to 0. Whenever zero air voids, degree of saturation equal to 100%. So normally the voids are filled either with the air or with the water. When the air voids are 0, then that soil is containing total uh, S is equal to 100%, 0 air voids, and 10% moisture content of the soil, W equal to 10%. The dry density would be, what is the dry density for the soil? It is very recent question 2019, and you know that whenever a question is asked for dry density, the immediate required formula is gamma D equal to G gamma W by 1 plus E. But observe the various unknown parameters. Here E is not known. To get E value, another formula S is equal to WG by E. So basing on this formula, first find out E and then calculate the gamma D value. So it's another great question. All questions are completely basing on the basic conceptual relations only. So the next question, the porosity and degree of saturation of soil sample are 0.7 40%. So porosity N is equal to 0.7, degree of saturation S is equal to 40%. In a 100 cubic meter volume of soil, so volume of soil, total volume is V equal to 100 cubic meter. The volume of air is how much quantity of air present in the soil sample. So volume of air is how much. So these are the three parameters given: porosity, degree of saturation, and total volume of the soil sample. What is the volume of the air? So what is the volume of the air? Volume of the air means total volume of voids minus, you can look at last. Volume of air will be equal to volume of voids minus volume of water. That means if you know the quantity of water present in the soil and if you know the total voids, we can find out the volume of air. So for this, what you do is you just find out the total volume of voids. So accordingly, N is equal to volume of voids to total volume. This is the basic definition of the porosity. So from this, volume of voids equal to, volume of voids is equal to N into V. N is 0.7 and V is 1000. So it is 70 cubic meter. That means volume of voids will be equal to 70 cubic meter. Out of 100 cubic meter of soil sample, 70 cubic meter of volume occupied by the voids. And S porosity, S degree of saturation, you know, volume of water by volume of voids. And degree of saturation also given 40%. So basing on this, find out the volume of the water. Volume of the water equal to S multiplied by volume of voids. So S is known 40%, volume of voids 70 just calculated, and volume of water is 28%. Once the volume of water is known, volume of voids also known, then volume of air will be equal to the difference of these two. So it is completely, a question is related to the basic definitions of porosity, degree of saturation, and also volume of voids. Is another question, very recent question. Next one is another question from GATE in 2015. A 588 centimeter cubed volume of moist sand So a 588 centimeter cubed volume, V equal to 588 centimeter cube. Weighs 1010 grams. So total weight is 1010 grams. If the dry weight is 918 grams, WD 918 grams, and the specific gravity of soil solids is 2.67. Assuming the density of water as 1 gram per cc, the void ratio is. So all these are the parameters given: total volume, total weight, dry weight, and specific gravity, gamma W are known, and what is the void ratio. So whenever a question is void ratio and some data is given, you can always observe gamma D equal to G gamma W by 1 plus E, and accordingly the unknown parameter. So from this data, you can find out gamma D. Gamma D equal to WD by V. Weight, dry weight of the soil by total volume of the soil. So it is 1.561 gram per cc. And substitute this value in the known equation, you will get the void ratio. Okay. Next question. I'll go a little bit fast because several questions are there, and we can observe it later. And I will skip some of the simple questions. This is a certain soil has the following properties: GS equal to 2.7, that is specific gravity of the soil solids, porosity 40%, and water content 20%. The degree of saturation of the soil is. So the values given is GS. GS means specific gravity of the soil solids. The specific gravity of the soil solids or simply specific gravity, both are one and the same. And porosity 40%, water content 20%, degree of saturation is unknown parameter. And once the degree of saturation is unknown parameter, the related equation is S is equal to Wg by E. So this is the formula to be obtained. Once you got the idea of this formula, observe the various unknown parameters. Unknown parameter is E. Again, E value can be found by knowing the porosity. E is equal to N by 1 minus N, and E is 0.667. Substitute this value in the formula, you will get it. It's a routine problem. Next question. In its natural condition, a soil sample has a mass density of 1.980 kg. So W is equal to 1.980. W equal to 1.980, and volume of 0.001 meter cube. So weight is given, volume is given in terms of the meter cube. After being completely dried in oven, the mass of the sample is, so 1.800 is the dry weight of the soil sample, 1.80, complete dry weight. Specific gravity is given 2.7. Unit weight of water is given 10 kilonewton per meter cube. What is the degree of saturation? It's also routine. Degree of saturation means go for the equation S is equal to Wg by E. And before that, gamma D equation, G gamma W by 1 plus E. It's also a routine problem for solving the question basing on the very preliminary relationships of the soils. So next question, the water content of saturated soil, and the specific gravity of soil solids were found to be 30% and 2.7. Small w 30%, G 22.7 given. Assuming the unit weight of water to be 10 kilonewton per meter cube, gamma W given. the saturated unit weight and void ratio of the soil are. So we need to find out saturated unit weight. So gamma saturated is how much? And again void ratio. You know gamma saturated, the formula G plus E by 1 plus E. But here E value is not known. So you have to calculate the E value and then substitute. So for getting obtaining the E value, you know S is equal to WG by E. So E is equal to WG by S. And from this S is equal to 1 already given water content of a saturated sample. In the problem itself it is given saturated sample S is equal to 1. So in this formula by substituting water content and G, void ratio will be obtained and substitute the void ratio in the required formula. So you got both void ratio and also saturated unit weight in a simple formula. Next one. A saturated soil mass has total density. Total density means it is always bulk density. Gamma equal to 22 kilonewton per meter cube. And a water content of 10%. W 10%. The question is the bulk density and dry density of this soil sample are. So what is the dry density? What is the bulk density? Here total density means itself is a bulk density. In the problem given, a saturated soil mass has a total density. So saturated mass has a total density means it is the bulk density of the saturated soil. So gamma bulk is 22. So you can look at the answer, gamma B is 22 without any calculations. And another thing is dry density of the soil. So you know the relation dry density and also bulk density related by the equation gamma D equal to gamma by 1 plus W, and accordingly it is 20. So option is 22 bulk density and 20 dry density of the soil sample. Next, the ratio of saturated unit weight of saturated means S is equal to 1. Ratio of saturated unit weight to dry unit weight of soil is 1.25. So you can write it gamma sat by gamma D equal to 1.25. It is given. If the specific gravity of the soil solids is 2.56, so specific gravity, either you can write GS or simply G. Specific gravity or specific gravity of soil solids, both are one and the same. It is 2.56. The question is, what is the void ratio? What is the void ratio? So you know gamma set formula G plus E by 1 plus E gamma W. You also know gamma D, G gamma W by 1 plus E, and divide 1 by the other. Gamma set by gamma D will be finally G plus E by G, and after substitution you will get the void ratio. So here it's a question. Question is indirect, but whatever the question, you always write the given data and observe what are the parameters to be found. Automatically you will get the solution. Next question. It's a simple. I am skipping. Another question. A borrow pit has a dry density of 17 kilonewton per meter cube. So you can see there are two things. One is soil from the borrow pit. It is having gamma D1 17 kilonewton per meter cube. How many cubic meters of this soil will be required? So what is the volume of the borrow pit soil V1 required to construct embankment of 100 cubic meter? So volume of the embankment V2 equal to 100 cubic meter with a dry density of 16 kilonewton per meter cube. So already you know the relation between volume of the soil and also dry density of the soil. Volume is always inversely proportional to the dry density. So you know here V1 by V2 equal to gamma D2 by gamma D1. Volume is always inversely proportional to the dry density of the soil sample. Already it is derived earlier, and there you can use it simply the final equation and substitute the fourth parameter. So here V1, V2, gamma D1, gamma D2, in all these four parameters, only one parameter V1 is not known. You can obtain the V1 value. And it is a simple one. E is given, and what is the porosity? The next question: a soil sample in its natural state has mass 2.29 kg. So that means weight of the soil 2.290 kg, and volume 1.15 into 10 power minus 3 meter cubed. Volume of the soil. Weight of the soil is known. Volume of the soil is also known. It is in a natural state. After being oven dried, that means the entire water will evaporate with the oven dried. The mass of the sample is 2.035. This is called the dry weight of the sample. Dry weight of the sample is 2.035. We can call it as dry weight of the soil sample, or otherwise weight of the soil solids. Weight of the soil solids. And the specific gravity of soil solids is 2.68. The void ratio of the natural soil is. So various parameters given. Weight of the moist soil given, volume of the moist soil given. Basing on these two, you can find out the unit weight of the soil sample. And since dry weight is given, you can also find out the water content in the soil sample and other parameters. So just relate the various equations. Finally, you need to find out what is the void ratio of the soil sample. So you can move with the fundamental concepts, or you can also move with the direct formula. So you are familiar with the direct formulas. You can look at here. Weight of the soil sample given, volume is given, dry weight is given, specific gravity given. Basing on these you can find out what is the water content present in the soil. W equal to total weight minus WD. It is called the weight of water. W minus WD is weight of water divided by weight of the solids into 100. This is the simple water content equation, and accordingly 12.53% of water available in the soil sample. And what is the unit weight of the soil? Dry density. Dry density will be dry unit weight, WD, dry unit weight by volume. So accordingly you will get a dry unit weight. And whenever void ratio is the unknown parameter, and some other parameters, particularly specific gravity and gamma W given, always use gamma D equal to G gamma W by 1 plus E. So it is a routine formula for computing the water content in the soil present and dry unit weight of the soil, and substituting those two in gamma D equation, you will get E equal to 0.53. So this is directly you can calculate based on the known formulas, or otherwise you can also calculate the same by means of the concept. You want void ratio. What is basic definition of void ratio? Void ratio is volume of voids by volume of solids. If you know the volume of voids and volume of the solids, the ratio itself is the void ratio. So in this formula, in this problem, you can look for how to calculate volume of voids and how to calculate volume of the solids. So for that, specific gravity basic definition is gamma S by gamma W, and gamma S means specific gamma S means what is gamma S? It is density of the soil solids. Density of the soil solids. that is Ws by Vs, weight of the solids by volume of the solids. And basing on this, you can find out gamma s. Gamma s will be equal to G multiplied by gamma w. You know, G multiplied by gamma w. G is known 2.68 given, and gamma w 9.81, and accordingly gamma s is known. Once gamma s value is known, gamma s means density of the solids. Density of the solids. Density of the solids is known. By knowing the weight of the solids, you can find out the volume of the solids. You can find out the volume of the solids. Volume of the solids equal to Vs equal to weight of the solids by gamma of the solids. So basing on this, you can find out Vs value. Once Vs is known, what is volume of voids? Volume of voids is total volume minus volume of the solids. So you will get volume of voids. Once volume of voids known, volume of solids known, you can calculate the void ratio of the given soil sample. So it is always better to proceed with the known generalized relations, because for this problem you need not to go look into the basic concepts. You always observe the associated formulas for computing void ratio and also water content. It is very simple for completing the problem. So always for any problem you can solve by means of the basic concepts or by means of the known formulas. Okay, and as you can look at it, these are the simple. Okay, I'll skip some of the problems. It's also a simple one. That's all. You can look at here. For a sand of uniform spherical particles, the void ratio in the loosest and the densest states are respectively. Already I told you in the theory, when the spherical particles are arranged in a cubical array, the maximum void ratio is 0.91. And when the spherical particles are arranged in a diagonal way, the void ratio is minimum, that is 0.35. And void ratio of all spherical particles in any of the direction varies from 0.35 to 0.91. So with this all get questions are over regarding the first chapter, and all these questions are very simple in nature. Once you remember almost 10 formulas and also some simple basic concepts, you can attempt and you can get perfect solution in any of the related questions in this particular chapter. Now let us go to some other next topic. Let us go to the next topic. Index properties of soil. So already we have seen two different topics. One is formation of soils or origin of soils. The second one is basic definitions and relations. Now let us see the various index properties of the soil. So normally for a soil, different types of properties it will acquire. One is index properties, which are normally related to the physical parameters like grain size distribution, relative density, Atterberg limits, etc. And other type of properties are the engineering properties. Engineering properties are related to the various parameters like coefficient of permeability, cohesion, angle of shearing resistance, etc. will come under engineering properties. Let us see completely the index properties of the soil. And normally here index properties also can be classified again into two different types. simply identification and classification of soils, and also rough estimation of its engineering behavior. So, by understanding the all engineering properties, the complete behavior of the soil is known. But prior to that, by observing the index properties or physical phenomena, we can also estimate how the soil is going to behave when it is under several different types of loads. And basically, index properties of soil can be divided into soil grain properties and soil aggregate properties. Soil grain properties particularly depends on the formation of soil, how the soil will be formed. It is by means of physical weathering or chemical weathering or organic decomposition, etc. Depending upon it, it is going to change. Particularly soil grain properties. So soils are containing its perfect grain, and normally it is always associated with the coarse grained soils. Coarse grained soils. Here, the analysis of coarse grained soils is completely depending on the size of the soil, what is the specific gravity of the soil, what are the different shapes of the soil associated in it, and also the various mineralogical classification. And you can look at the grains look like this. So it is more angular in nature and less angular, or we can call it as subangular in nature. Sub-rounded, it is not rounded, it is just towards rounded shape, whereas it is almost round but not perfect rounded shape, and it is well rounded. So normally coarse grained soil sample contains the grains having different shapes of the particles. So any particle is one among the several particles. Here there are some advantages and also disadvantages of different shapes of the particles. Normally the bulk shape means we always observe what is the length of the particle, what is the width of the particle, and also the thickness of the particle. If all the three dimensions, length, width, and thickness of the particle are almost same, then we can call it as a bulky grains or bulk grains. And these bulk grains will support the loads under static condition. And whenever these bulk things are there, it will always susceptible to vibrations, and large deformations will take place due to vibration. And if anybody wants to compact the grain soils, post grain soil, the perfect compaction is by means of the vibration. Because of the vibration, the soil gets rearranged and a lot of deformation takes place. And in this angular aggregate will always have less strength, but it has little displacement. Whereas well-rounded aggregate particles are having high strength and also low displacement. You can look at the influence of angularity. The particles with high angularity, if the angularity is more, it resists the displacement. The displacement of the angular particulate soil is very less, but it is more tendency for failure. So fracture will occur because of loads acting on the soil, but it always resists against the displacement. And in case of rounded shape of the particles, and it won't crush easily. That means it will take maximum load, but it always have tendency to move to roll. So that means displacement of a rounded particle is always a danger, but it is always susceptible to taking the loads, compressive loads. Then flaky grains. Flaky grains means it is almost plate-shaped grains. The thickness is very small compared to the other two dimensions. Then it is called the flaky material. So these flaky materials will always crushed very easily because one dimension is very small, other two dimensions are considerable. And similarly, when soil contains more of flaky materials, it always resists the vibrations. You can look at here, the flaky materials are more stable when vibrations occur in the soil. Another one is needle shape of the grains. The name itself is understood needle shape. So that means the length of the grain is more when compared to the other two dimensions of the soil. Then specific gravity. So already you have seen specific gravity in the basic definition. Specific gravity is the ratio of the unit weight of soil solids to the unit weight of water. Unit weight of soil solids to the unit weight of water, or otherwise weight of soil solids to the weight of water of same volume. Of same volume, it is called the specific gravity of soil, and it is very useful for various applications for determining the void ratio, degree of saturation, unit weight, particulate size by wet analysis, critical hydraulic gradient, for all other properties, the specific gravity property is more important in the soil. And there are several ways for computing the specific gravity of the soil. Here, let us not spend much time here. If you are able to understand what are the various methods that are to be adopted for finding the specific gravity of the soil is more important, and detailed procedures, methods not required for competitive or gate examinations. So density bottle method is the one. It is the questions will be like this. For example, density bottle method is suitable for finding the specific gravity of which type of soils. That is the question. So you can look at here. It is most suitable for fine grained soils having more than 90% passing through 2 sieve. So that means if the size of the particles are less or for fine grained soils, density bottle method is always gives more accurate value. That line is enough, not more than that. Measuring flask method. Measuring flask method also suitable for fine grained and also medium grained soils. So this line is more important for any of the competitive examinations. Then picrometer, which is most popular method that we are using in the laboratory of all engineering colleges, and it is used for the coarse grained soils. So remember that in your laboratory you have done finding the specific gravity for a coarse grained soil, or particularly the sand, or sometimes sandy soils. So sandy soils specific gravity can be found more accurately by means of the picrometer method. And in this case, oven dried sample is to be taken. You can look at the diagram. Picrometer is some shape, and soil sample, dry sample is to be taken for finding the specific gravity of the soil. Here it is picrometer plus dry soil. So this entire soil is consisting of only one constituent material, that is soil solids. There is no water and only air present. Air present, no water. And look at how the picrometer will be used for finding the specific gravity. So in the first diagram, it is weight of the empty picrometer. Weight of the empty picrometer, which we can call it as W1. Then pycnometer plus dry soil, whatever the dry soil that was that taken in the previous diagram is W2. Then pycnometer plus soil sample and completely filled with water is termed as W3. And another measurement, fourth one is pycnometer plus total water. Complete water is called W4. And with these four different weighing measurements, weights, you can find out the specific gravity. You know the specific gravity. What is the specific gravity definition? Weight of the solids divided by weight of the water of the same volume So that means in the numerator W2 minus W1 is the weight of the soil solids. W2 minus W1 means, look at here, W2 minus W1 means you will get weight of the soil solids. Weight of the soil solids. And in the denominator, it must be weight of the water equivalent volume of the solids. You can look at here in the second diagram, the solids occupy only a small amount of volume. It occupies only some small amount of volume. In the same amount of volume, if water occupies, how much is the weight? So that weight is called the weight in the denominator. Weight in the denominator. So numerator is weight of the dry soil. In the denominator is weight of the water of volume equivalent to that of the soil solids. Soil solids. You can look at W4 minus W1. What is W4 minus W1? W4 minus W1 means the pycnometer, what entire volume of water, entire weight of water will be obtained. W4 minus W1 means total weight of the water filled in the pycnometer is known. So first term is total weight of water occupied in the pycnometer. W3 minus W2. W3 minus W2 means water other than the solids. Water occupied in the pycnometer other than the solids. Water occupied in the pycnometer other than the solids. So first term and second term difference is weight of the water occupied in the same volume of the solids. In the same volume of the solids. You know this entire water minus this entire water will give you water occupied in the soil solids. Water occupied in the soil solids. So that is this formula. W2 minus W1 by this. So always do not try to by heart it. Try to understand the concept here. I'll tell you once again because it's an important concept. W2 minus W1 means weight of the dry sample. Weight of the dry sample. And the denominator must be weight of the water for the same volume of the solids. What is the weight of water for the same volume? W4 minus W1 means total volume, total weight of the water occupied in the pycnometer minus W3 minus W1 means weight of the water occupied in the pycnometer other than the solids. Other than the solids. The difference of these two will be water occupied in the same volume as that of the solids occupied in the pycnometer. So this is the basic definition concept, and accordingly for the case of simplification you can write W2 minus 1, 3 minus 4 and somehow you can remember. But always try to understand the concept and try to remember. So W1, W2, W3, W4 already designated. And this specific gravity value is always to be computed at 27 degrees centigrade. If the temperature is more, density, specific gravity changes, or temperature is less, specific gravity also changes. Sometimes what is going to happen is, when the medium used as water, and for some period, within a little amount of time, the entire water may not penetrate completely into the solids. Originally we are taking a solid, complete dry solids, and when you keep water, sometimes a part of the solids may not be in wet condition. So in such case, you will get the wrong value. So correct value will be obtained only when all the solids are completely saturated. When a part of the solids are not saturated, you are not going to get exact value of the specific gravity. So in such a case, we normally use kerosene for finding the specific gravity. Kerosene for finding the specific gravity, because kerosene is having more dispersion capacity than water, and kerosene will penetrate each and every particle of the soil solids within no time. The formula will be modified as it multiplied with the kerosene specific gravity. Formula is same, but formula is same because original specific gravity formula is weight of the soil solids divided by weight of the water of the same volume. Since it is weight of water and we are not using water, we are using kerosene. So we are converting it into the equivalent value by multiplying GK, the specific gravity of the kerosene. And sometimes normally it is always to be reported at 27 degrees centigrade, and it may be tested at different temperature also in the laboratory. In such cases, what we do is, GT1, you can look at the last one, GT2 equal to GT1 into GWT2, GWT1. So here GT1, GT2 are the specific gravity of the soil samples at temperature T1 and at temperature T2 respectively. If the soil specific gravity found at temperature T1, you can find out the soil specific gravity at temperature T2 by using the relation. That means specific gravity of water at T2, specific gravity of water at T1. So using this relation, you can find out the more accurate value when the test is conducted other than 27 degrees centigrade. So sometimes what we do is GT is the test temperature, specific gravity of the soil sample at any temperature T. But original specific gravity must be calculated exactly at the temperature of 27 degrees centigrade, and this is the equation associated with the temperature at any specific gravity at any temperature and specific gravity corresponding to 27 degrees centigrade. Next, particle size distribution. Normally, the soil contains several different sizes. We can classify it as coarse grained soils and also fine grained soils. When the soils are coarse grained and cohesion is less, it is always comfortable to go for sieve analysis. Sieve analysis is suitable for coarse grained soils. And when cohesion is less, then you will get exact results based on the sieve analysis. And it is only for the cohesion less means for sandy soils always sieve analysis is preferable. And for the soil containing fines, and those fines are having with cohesion. When the soil fines are having cohesion, it adhere to the other particles, and final analysis by means of the sieve analysis, you will not get exact value. For exact value of the fine grained soils, it is always better to go for wet sieve analysis. Different methods are available for wet sieve analysis, and that is always suitable for fine grained soils. Sometimes the questions are very simple. Sieve analysis is used for option A coarse grained soils, B cohesionless soils, B cohesive soils, fine grained soils. Like that, several options may be asked in the competitive examination. Next, sedimentation analysis suitable for fine grained soils finer than 75 micron sieve. 75 micron means 10 power minus 3 meters. 75 into 10 power minus 3 meters. 75 micron is not micron size. Sedimentation analysis is can also be done for the fine grained soils, and that is based on the Stokes law. This Stokes law is valid only when the particles are spherical in nature, and this law is particularly suitable when the soil particles are between zero point 0.2 mm and 2 micron. Between 0.2 mm and 0.2 micron, that is 0.2 mm to 0.0002 mm. So these are the four different types of analysis that can be carried out for the particle distribution of coarse grained soils and also the fine grained soils. So accordingly, we can classify in general gravel. The size varies from 80 to 4.75 mm. When the size is more than 4.75 mm, it will be called as a gravel. And sand means when the size is between 75 micron and 4.75 mm, the type of soil is called the sandy soils. And silt means between 75 microns to 2 microns. 75 microns and 2 microns, the material is called, the soil is called the silt. And clay less than 2 micron. Less than 2 micron. So you need to remember 2 micron to 75 microns, 75 micron to 4.75 mm, 4.75 to 80 millimeter. So these are the general classification that are to be used for the all practical engineering purposes. And sometimes a question may be very small. The size of the silt varies from option A, B, C, D. A soil is said to be clay when the size of the particle is less than 0.02 mm, 0.2 mm, 0.002 mm, like that several options may be given. So each and every point is very key and important. Sedimentation analysis. Wet analysis. So for fine grained soils, always sedimentation analysis will be preferable, and for this Stokes law is used for computing the various parameters like terminal velocity, size of the particle, shape of the particle, weight of the particle, and all other factors. But this Stokes law is always valid when the particles are spherical in nature and having the same specific gravity. Sometimes the soil may contain different specific gravity of the particles. If the specific gravity of the soil particles are different in nature, then the Stokes law is not valid, and we are assuming that all the particles are having the same origin, having same specific gravity and spherical in nature. And normally the range for validity of the Stokes law given 0.22, just you can see 0.2 to 0.2 microns, 0.2 mm to 0.2 microns. So in this range only it will give exact results. For sizes greater than 0.2 mm, turbulent motion is set up. So while settling down the particle, the size more than 0.2 mm, the action while going down, it is having turbulent motion, and the Stokes law is not valid. Whereas for the size of the particles less than 2 microns, the problem is Brownian motion is going to set up, and accordingly some flux will form and it will not give exact result. So this is the range of the particles where the Stokes law is valid. And assumptions, then terminal velocity. So this Stokes law is also being used in case of sedimentation tanks in environmental engineering also. The same theory, same formula is valid there. So Vs settling velocity equal to G by 18, G minus 1 by d square by nu. So here Vs is settling velocity of the particle, G the acceleration due to gravity, capital G specific gravity of the solids, small d size of the particle that is settling down, and nu kinematic viscosity of the soil. So by knowing all these parameters, we can find out the terminal velocity, and accordingly we can find out the proportion of the soil sample. Then for fine-grained soils can also be analyzed by means of pipette method, and normally in the pipette method sodium hexametaphosphate of 33 grams and 7 grams of sodium carbonate is distilled in distilled water to make up 1 liter of solution. It will be used for obtaining the classification of the soil sample. And here it is very simple, and it will take more time, and very accurate weighing balance is required, and depending on the various parameters that are involved, it is always gives less accurate, but more appropriate values will be given. So in this only, just remember, a solution is to be prepared with sodium hexametaphosphate of 33 grams and 7 grams of sodium carbonate to prepare 1 liter of solution. That is important. And also pipette method is used for analysis of the soil particulate matter of the fine grained soils. That is enough. Then hydrometer analysis. Hydrometer analysis is also based on the sedimentation analysis. And there is a little bit difference in taking the observations of pipette method and also hydrometer method. In case of pipette method, we always consider 10 centimeter sampling depth, whereas in case of hydrometer test, the sampling depth increasing continuously as the time interval. And the most important thing here is the various corrections to hydrometer readings. Once the readings are noted down, all those readings are not of exact because of the so many factors involved. So here correction for the reading C equal to Cm minus Cd plus or minus Cd. So Cm is meniscus correction. So always in the hydrometer, the top surface is not horizontal. There must be some correction, and it is always positive since the reading is on the upper level of the meniscus. And CD, deflocculating agent correction. So whenever agent will be used, and here the density of the suspension increases, and accordingly it is the correction is always negative. and temperature correction. Temperature correction may be plus or minus depending upon above 27 degrees centigrade or below 27 degrees centigrade. If the temperature is more than 27 degrees centigrade, correction due to for temperature is positive, and less than 27 degrees correction is negative. So these are the some of the methods where the procedures detailed discussion is not required, and only outer line of the methods are sufficient for this particular competitive examination. Next, particle size distribution. Coarse grained soils will always be analyzed for the particle distribution by means of the sieve analysis. And what are the various sieves that are associated? It is associated from 2 microns to 4.75 millimeters, and if the size is more, you can also use more size of the sieve. And finally, after some calculation, we always draw the diagram relating to percentage of fines, and also particle size, percentage of fines and also particle size. Here it is taken on the log scale. X-axis is taken on the log scale. That means log of the particle size. For example, if 1 mm size of the sieve is used, log 1 is the value, or 10 mm size of sieve is used, log 10 is the appropriate value, or 4.75 mm, log 4.75. So accordingly, the values are to be taken on the x-axis. Particle size in millimeters, which is under the log scale. Whereas in the y-axis, percentage finer value. For example, if the all particles are less than 4.75 mm, what is going to happen when the soil is pouring over 4.75? Entire soil will pass through. That means 100% of the soil is passing through 4.75 mm sieve. So here percentage finer means over a 4.75 mm sieve, percentage finer is 100%. That means we always look at the passing material. How much percentage of material is passing through a particular sieve. And basing on the various calculations, that means normally what we do in the laboratory, serial number, size of the sieve, weight retained on the sieve, then cumulative weight retained, cumulative percentage weight retained, then percent passing through. And graph is drawn between percent passing through versus size of the particle. Particle size on the x-axis and the y-axis percent passing through. And basing on that, if the graph is drawn, several curves will come into picture. Several curves. You can look at here. First one is 0.001 mm on log scale, 0.01 mm on log scale, 0.1110 mm. It is on the x-axis particle size. That means near origin, the size of the particles are less, and as it is moving away from the origin, the size of the particles are increasing. That means if the total curve is on the left side, it is always fine grained soil. You can look at green color curve. This green color curve is the graph obtained from the sieve analysis, and it is always called as fine grained soil because the particle sizes are very fine in nature, and the curve is limited only on the left portion. So that's why it is called the fine grained soil. Whereas red color karu, which is on the extreme right, it is most of the material on this is large in size. That is 1 mm or more than 1 mm size. So that means the nature of the particles of the soil is coarse grained soil. And remember, when a graph is drawn on a percentage passing through versus particle size on the x-axis, if the curve is on the leftmost side means the fineness of the finer particles are more in the soil. Whereas the curve represents on the extreme right, the coarse particles represent in the soil are more. Extreme right. So this is how the coarse grained soils and fine grained soils can be distinguished based on the position of the curve, whether it is towards extreme left or towards extreme right. If it is extreme left, fine grained soil; extreme right, coarse grained soil. And there are some other curves. You can look at the curve. You can look at this curve, almost S-shaped flat curve, almost flat S-shaped curve. Flat S-shaped curve represents that all sizes of the particles present in the soil. Then such a soil is called the well-graded soil. When all the different sizes of the particles are existing in a particular soil, the soil is called well-graded. Well-graded. All sizes of the particles are available in the soil. Whereas on the extreme left, only fine size of the material available. On the extreme right, only coarse material are available, whereas on the flat S-shaped curve, all the different types of sizes of the materials are available in the soil, and that's why it is called well-graded soil. Well-graded soil. And next, bottom blue color, you can look at this bottom blue color. There is a horizontal curve. Horizontal curve means it is a void. There is no material in this range. When a curve represents some horizontality, in that area, in that space, there is no material containing between the two horizontal lines. That means particularly for this curve, there is no material between 0.01 and 0.1 millimeters. And fine materials available, coarse material also available, and because of the horizontality in the curve at some place, that is called the gap graded soil. That means there is no a particular soil. Normally, well graded soil means all sizes of the particles must be available. But here, some portion of the soil particles are not available, so there is a gap. So that's why it is called gap graded soil, or sometimes skip graded soil. So some size of the particles are skipped in the soil. That's why it is called skip graded soil or gap graded soil. So the other blue color is, it is almost vertical in nature. When it is almost vertical in nature means only single size of the particles present in the soil. Single size of the soil present in the soil. That's why it is called uniform graded soil. Yeah, that means all the sizes of the soil are almost same. That's why this curve represents vertical. That's why this curve represents vertical. In the examination, sometimes the graph may be given, and graph may be represented A, B, C, D, 5 different curves, and a question may be asked, or matching may be given, A, B, C, D. On one side, other side it may be fine grained soil, coarse grained soil, uniform graded soil, well graded, gap graded, etc. So you should be able to identify such a type of soils. Or sometimes without the graph, theoretical questions also can be asked. So I will briefly explain once again without much time. When a curve is extreme left, then it is called fine grained soil. When the curve is extreme right, the type of soil associated with the curve is coarse grained soil. When the curve is having a flat shape of S, flat S curve, then it is well graded soil. It contains all sizes of the particles. When a curve is horizontal, when a part of the curve is horizontal, then it is called the gap graded soil. The soil contains gap graded or skip graded. When a curve is almost vertical in nature, then the type of soil included in it will be uniformly graded soil. That's all about the overall concept of it. And of course, it is completely explanation of that particular curve, and you can read later. For sandy soils, coefficient of uniformity and coefficient of curvature are the two different parameters expressed for finding whether the soil is uniform, gap graded, well graded, etc. It will give a rough idea for the different types of soils. So one important definition is coefficient of uniformity, and it is a measure of particle size range. For measuring the particle size range, CU is appropriately used. So coefficient of uniformity is D60 by D10. D60 D10. D60 means size of the particle below which 60% of the soil is finer than this size. It's a little difficult to understood, but I will explain very clearly once again, and also with the numerical problem for understanding the total concept. D60 means, D means diameter or size of the particle below which 60% of the material passing through that size. Similarly, D10 means size of the material below which 10% passing through it. Below which 10% passing through it. So, okay, to understand D60, D10, I'll explain a simple problem. These are the various sieves that we normally use for coarse grained soils. 4.75 mm, 2.36, 1.18, 600, 150. Assuming that the weights after sieving of the sample, the weight retained in various sieves are 4.75, 160, 140, 60, 140. Assume that these are the weights retained on the sieves. And next one is cumulative weight retained. So 160 and 160 plus 140, 300, 360, 360, 360 and 40, 400, and total weight is 400 grams. When 400 grams sieved, this is the appropriate values obtained after sieve analysis. And basing on the cumulative weight retained, find out the cumulative percent weight retained. So total weight is 400. So 160 by 400 into 100 is 40%. And 300 by 400 is 75%. 360 by 400, 90%. 400 by 400, 100%. That means here cumulative percent weight retained. Cumulative percent weight retained is 100% in all these, whereas here 40, etc. So when the weight retained is 40, what is the material passing? Material passing is 60%. The meaning of it will be, in a 4.75 sieve, 40% of the material retained. And what is the passing percentage material remaining? 100 minus 40, 60. Similarly, in a 2.36 sieve, 75% of the material retained means 25% is passing through 2.36. And similarly, in 1.18, 90% of the weight retained and only 10% is passing. Only 10% is passing. Now look at this definition. Already I told you what is the meaning of it. 10% of the material is passing. Percent passing. It is 10% of the material passing. Whereas here 60% of the material passing. What is the meaning of it? D10 means size of the material such that 10% of the material is finer than that size. Say for example here, finer than that size means passing through 10%. So here percent passing is 10%. What is the associated size? 1.18. That means in a 1.18 mm size of sieve, 10% of the material is passing. 10% of the material is passing. So D10 equal to 1.18 mm. D10 equal to 1.18 mm. That means D10 means size of the material below which 10% is passing. Below which 10% is passing. So corresponding to 10% passing, the size of the sieve is 1.18. So D10 will be equal to 1.18. That is the meaning of it. Similarly, you can look at here where the 60% passing, 60% is passing at this level, and that is corresponding to the sieve size 4.75. So D60 equal to 4.75. D60 is 4.75. I'll give you the basic meaning of it once again. D60 means size of the material below which 60% of the material passing. And D10 means size of the material below which 10% is passing. So when 10% is passing, find out the size 1.18. When 60% is passing, find out the size 4.75. Accordingly, CU will be 4.75 divided by 1.18. It is sometimes it may be a numerical question asked for the examination. You know the meaning. T60 means particle size in mm such that 60% of the soil is finer than this size. D10 means particle size in mm such that 10% of the soil is finer than this size. D10. It is a D10. Normally D10 is called effective size or effective diameter. That means in the previous example, what is the effective diameter of the soil means 1.18 mm. And once the CU value computed, normally it is always more than 1 because D60 is always more than D10 and naturally CU is always more than 1. So once CU values are known, depending on the numerical value, we can call it as uniform soil, well-graded soil, well-graded sand. Another definition related to particulate distribution is the coefficient of curvature. Coefficient of curvature is CC D30 square by D60 D10. Already you have seen earlier D60 and D10. Now it is D30. D30 means same meaning. Particle size in mm such that 30% of the soil is finer than this size. And for uniform soil, CC equal to 1. And for well-graded soil, coefficient of curvature varies between 1 and 3. So these are the two important equations from the examination point of view. Then soil aggregate properties. In this we are going to see the various parameters to be found. That is water content, institute density, density index, consistency limits or outer work limits. So let's go a little bit fast because it's not of so much of important. Water content. There are several methods are there. Already you know the basic definition. Where water content is weight of the water to the weight of soil solids. Weight of water to the weight of soil solids. That is water content. So for this, normally what we do is, initially it is a laboratory method and it will give most accurate method. And normally what we do is, initially we take the some soil sample, moist soil sample, and weigh it, and later it is kept in oven for dry condition, and again weigh it. That is called the dried weight. The difference of these two is the water lost due to evaporation in the oven dried, and finally water content W will be equal to weight of the water to the weight of the solids. It's a very simple one. Already numerical problems also discussed earlier, and no much explanation is required. So here you can look at W equal to WW by WD, weight of water by weight of dry weight of the soil, and that is total initial weight minus WD by WT. So that is one method, and several methods, other methods are there. Just understand the names and how it will be used and where it will be used, and whether it is quick test, it will give accurate results or not. That is more than enough in case of computing the water content by means of different methods. One is, second one is calcium carbide method or rapid moisture tester method. Just remember the name itself, rapid moisture tester method. That means moisture testing will be done quickly. That's why it is called the rapid moisture tester method, and it will be done within 10 minutes. The basic principle here is carbide reagent reacts with the soil water and it forms acetylene gas, and this acetylene gas will give or will exert pressure on the soil, and accordingly water content can be determined. If more water present, more reaction with the carbide and more amount of acetylene gas produced, and accordingly exerts more pressure, and based on the pressure the moisture will show automatically in the equipment. Then sand bath method. So here it is on a oven, on a pan of hot pan, keep some sand, and again over it keep the soil and heat it. So that what is going to happen, because of rise of temperature, the entire water will lost, and basing on that you can find out how much amount of water lost divided by weight of the soil solids. But while doing so, the temperature normally must be 105 to 110 degrees centigrade only, and depending on the type of material, we have to adjust the temperature also. For example, if the soil containing organic matter, and if the temperature is around 110 degrees centigrade, the entire material, entire organic matter is going to burn, and you may not get exact results. So depending upon the material present, whether the soil contains gypsum or any other material which affects with the temperature, and accordingly adjust the temperature. Normally for a soil containing gypsum and other characteristics of the soils. Sometimes temperature may be reduced to 60 degrees or 80 degrees, but long period. And another one is alcohol method. So here alcohol method is a very simple method. What normally we do is take a sample of wet soil and mix thoroughly with the alcohol and burn it. It's a open burning. It's a open burning, and after open burning, you will get the complete dry weight. So for quick results in the field where the equipment is not available, and this is one of the method to be adopted for the roads and also in several engineering aspects. And several indirect methods also there, pycnometer method, and it is also suitable for coarse grained soils. Already, while calculating, computing the specific gravity for the coarse grained soils, we require pycnometer, and the same pycnometer can also be used for finding the water content of the soil. But by using the pycnometer, already you should know the specific gravity of the soil solids. If you know the specific gravity of the soil solids, then only you can find out the water content by using this simple formula. And the various parameters W1, W2, W3, W4 are same as that of for specific gravity, except the soil is wet soil. In earlier case, for computing the specific gravity of the soil, we require only the dry soil. Whereas in case of water content present in the soil, we require always wet soil. Except this change, W1, W2, W3, W4 all are one and the same, and accordingly water content can be found indirectly by knowing the specific gravity of the soil sample. So it's a pictorial graph, already graph shown, already the diagram shown earlier. It's a empty weight W1 and pycnometer plus wet soil, because initially we are going to take some wet soil, and accordingly it occupies solids and also water, small amount of water, and then by keeping full amount of water and total water W1, 2, 3 and also 4, by using the simple equation we can find out the water content by means of the pycnometer method. And radiation method. And radiation method is extremely useful for water content, directly to get the moisture content in the field itself. And particularly when the radiation method is used, we can also obtain the more moisture content not only on the surface. We can also hammer blows, the entire core cutter is going down and it will be filled completely with the earth material, and the weight of the soil divided by the volume of the core cutter will give you the density, and it is a very simple direct field method. Then sand replacement method, it is another method used for fine grained soils or coarse grained soils. It is mainly used for finding the how much amount of soil is taken out from the ground. It will be obtained by filling the sand. That means replacing of the soil by means of the sand, and knowing the volume of the sand, we can get volume of the soil sample taken out, and accordingly we can find out the density by knowing the different equations. And of course rubber balloon method, normally it is not advisable, and balloon may not be completely penetrate into the soil because of irregular T in the soil, and just understood the names of various methods, not much required. Next, relative density or density index. So normally what we do is in the laboratory we are going to conduct experiment for finding the density. What maximum density, MDD, maximum dry density, and optimum moisture content. And similarly, in the case of field, how much percentage of density is obtained, or what is the relative density when compared to the original standard density. So that is to be computed using a simple relation and also equation. It is used for coarse grained soils or sands. Coarse grained soils or sands. So you can look at the diagram. You can look at the diagram. Here density index ID on y-axis, density index on y-axis, and on x-axis void ratio. You know, the density always depends on the void ratio. If the void ratio is low, if the void ratio is low, that is E minimum, the corresponding to that, the density will be the maximum. And maximum relative density is 1. Relative density means density of a soil in the field is compared with the standard density of the soil tested in the laboratory. So when field test density is same as that of laboratory density, then density index equal to 1. So that is possible when soil is compacted to E minimum. So voids are as minimum as possible. Density index or density ratio is 1. And when the voids are maximum in the soil, E equal to E maximum, then ID will be equal to 0. Relative density equal to 0. And for any void ratio, the corresponding density is called the ID. This ID varies from 0 to 1. 0 to 1. So depending on the amount of compaction and depending on the magnitude of the value of the void ratio, the density varies from 0 to 1. Accordingly, from this particular graph, if you take theta here and relate with the E maximum, E and also E minimum for finding ID value, you will get the simple equation ID equal to E maximum minus E by E maximum minus E minimum into 100. It's not difficult to remember, and I try to remember this because evaluating this formula in the examination is not so simple. So ID equal to E max minus E by E max minus E minimum. So E max means maximum void ratio when it occurs only in loose condition, when the soil is in loose condition. E minimum occurs when the soil is in a dense state and the value is minimum. And small e is the any natural state, void ratio of the natural state. So this is a simple formula and needs to be remembered. And also, you know, the density can be represented in terms of the density. The ID relative density can also be represented in terms of the densities. Like E values, E maximum, E minimum and natural void ratio. Here also there are different types of densities. Gamma D, natural gamma D. That means gamma D for a natural soil, the density is gamma D. For more compacted soil, the density is gamma D maximum. For less compacted soil, worst compacted soil and or no compaction of the soil, the gamma D minimum. So that means the soil is having its minimum possible dry density, maximum possible dry density and also dry density of the soil. So we can also relate with this, and this, no need, don't remember any of the formula related with the densities. You just understood the relation with the void ratios, E maximum, E maximum, E minimum. So E maximum, when will be, when E maximum, what is the density? When the void ratio is maximum, what is the density? density is always minimum. When E is maximum, density is always minimum. So what you do is, whenever E maximum occurs, you can write 1 by gamma D minimum. Here it is maximum, you write minimum. And E means 1 by gamma D only. E max means 1 by gamma D minimum. Because when wide ratio is maximum, the density is minimum. So that's why it is 1 by gamma D minimum. E minimum means 1 by gamma D maximum. So by knowing this relation wide ratio with the density index, you can also establish the relation in terms of the different densities, and after simplification you will get this. Don't try to remember this density relation, because whenever it is required, you can always get the final equation from the wide ratio known relation. You will substitute E by 1 by D, E max by 1 by gamma D minimum, E minimum by 1 by gamma D maximum. So with that you will get the two different formulae related to wide ratio and also the different densities of the soil. And of course, in any of the methods, these are the general formulas. Already you know gamma D equal to G gamma W by 1 plus E. So the wide ratio can be found only using original basic relations, and finally the density relation density ranges from 0 to 100, or otherwise we can call it as 0 to 1. When the density is 0, it is loosest state of soil, and when ID is 1, it is completely perfect dense sand or dense material, dense soil. And here, depending upon the ID value, we can classify the soil. Sometimes in the examination, he may give, question may be in terms of E minimum, E and E maximum, and answer may not be numerical. Answer may be A very loose, B loose, C dense, D very dense. So that means if you are able to understand the relation of all these numerical parameters, then only you can answer some of the questions. Though you know the formula, how to calculate ID value, etc., unless you know the denseness of the soil for various ID values, you cannot answer sometimes some of the questions. So when ID is less than 15, it is very loose. That means density, relative density is very small. Whereas ID is more than 85 means very dense soil in nature, and in between various other terminology. Then consistency of clays. Consistency of clays. So here in this consistency, we are going to deal all the Atterberg limits, the various limits that are associated with the soil when the behavior changes from one state to the other state. And it is used for fine grained soils, and everybody knows that you have done in the laboratory liquid limit, plastic limit, shrinkage limit, and all these limits are done for a fine grained material, particularly passing through 425 micron IS sieve. So that means these Atterberg limits are only for the clay soils, not for the coarse grained soils. Sometimes it may be a small question. Atterberg limits are to be carried out for which type of soils? It is only clay soils or otherwise fine grained soils. And here you should know the meaning of consistency of the soil. Consistency is the resistance offered by the soil against forces that tend to deform or rupture the soil aggregate. So whenever there is a possibility of deformation and rupture takes place, there must be some resistance against the deformation and also rupture, and that resistance offered or resisted against these forces is known as the consistency of the soil. And here consistency mainly depends on cohesiveness of the soil. And cohesiveness is only for the fine grained soils, particularly the clay soils. And due to the presence of cohesion and shear strength of the soil present, shear strength in the soil present. And while transmitting from one stage to other, that means by using different quantities of water in the soil, it may be initially in a liquid state. After some dried condition, it may come into plastic state, and then semi-solid state, and then solid state. So that means soil, clay or soil is same. Depending on the amount of water available in the soil, it may take different stages of consistency. That consistency may be in the liquid state, maybe in the plastic state, maybe in the semi-solid state or solid state. And these are the different stages where soil transform from one level to the other level, and various limits are called the Atterberg limits. And these Atterberg limits are liquid limit, plastic limit, shrinkage limit, shrinkage limit. And you should know at this juncture, since it is only for the clay soils, all the clay materials are having cohesive properties, and because of the cohesion, the clay soils are always possessing plasticity of the soil. Plasticity means it is a property of the soil which allows to be deformed without rupture and without rebound and without noticeable change in volume. So here what is going to happen whenever some forces are acting on the plastic soil, it allows to deform continuously without rupture and without any change in volume. So that is the unique property particularly for the clay soils. And let us look at a graph, a chart between water content and volume of the soil. You know that for the same grains of soil, if the proportion of the water is different, and the action of the soil and its associated properties are entirely different. So you can look at in the horizontal axis, it is water content. First one WS, shrinkage limit, WP, plastic limit, WL, liquid limit. Liquid limit, plastic limit, shrinkage limit, these are the three limits of the water content junctions where the state of the soil changes from one state to the other state. So when the water content is more, initially it is in liquid state. And when the water content is a little bit less, then it converted into plastic state. And if the water is still less, semi-solid state, and water is almost zero, then it is called the solid state. So these are the various states and also associated with the various liquid limits, and liquid limits are associated always with the water content. Now let us define what are the various liquid limits, how to define it. For example, WL. WL is the liquid limit. The definition, everything is basing on this diagram only. We need not worry about anything. So liquid limit is the water content at which the state of liquidity of soil changes from liquid to plastic condition. Liquid limit is the water content at which soil changes from liquid state to the plastic state. That is called the liquid limit, or otherwise Liquid limit can also be defined as it is the lower percentage of water, lower water content beyond which the soil changes to liquid state. You can also define in this way. Liquid limit is the lower water content beyond which any addition of amount of water the soil changes to liquid state. Or one more definition can be liquid limit is maximum water content above which the soil changes to liquid state. So you can define the liquid limit in terms of the liquid state. You can also define in terms of the plastic state, or you can define in terms of both plastic and limit state. I will tell you once again. Liquid limit is the water content at which the state of soil changes from liquid to plastic state. That's one definition. We are using both liquid and plastic terminology. Another one is with only liquid state. So that means in case of liquid limit, it is the lower limit of water content beyond which any addition of water, the soil changes to liquid state. Or one more definition, liquid limit is the water content below which liquid limit is the maximum water content below which the soil is in plastic state. Below which the soil is in plastic state. Like that, you can also define plastic limit WP. WP is the water content between plastic state of soil to semi-solid state of soil. So the similar type of definitions are valid for it also. So plastic limit is the water content at which the soil changes from plastic state to semi-solid state. Or otherwise, plastic limit is the minimum water content beyond which the soil changes to plastic in state. Or otherwise, plastic limit can also be defined as plastic limit is maximum water content for the state of semi-solid soil beyond which the soil converts into plastic state. All these definitions are basing on the state of soil on either side of the line. And similarly, shrinkage limit. You can look at this diagram. Initially, when the soil is in liquid state, as the water content decreases, the volume decreases continuously by means of sloping inclined line. And once it reaches WS, the line is perfectly horizontal. Line is perfectly horizontal means there is no change in volume of the soil from WS to dry state. That means once the soil reaches the shrinkage limit, there is no change in volume, even water reduces. That means if at all some water reduces, that water will be filled by means of air. There is no change in the total volume of the soil. There is no soil. So once again I will tell you, shrinkage limit is the water content at which the soil changes from semi-solid state to the solid state. This is one way of representing the definition. The other way is shrinkage limit is the maximum water content. Below which any reduction of water will not reduce change in volume. I will tell you once again. Shrinkage limit is the maximum water content below which the volume does not change due to even reduction of the water content. So that's why between dry state of the soil and WS, the soil volume is always constant. And at WS, at shrinkage limit, the entire soil is in saturated state. The entire soil is in saturated state. You can also define shrinkage limit with reference to the saturated state. Shrinkage limit is the Shrinkage limit is the water content at which the soil is completely saturated. At which soil is completely saturated. And even if there is any small reduction amount of water, the soil is not going to be completely saturated. So these are the various definitions related to liquid limit, plastic limit, and also the shrinkage limit. Liquid limit will be determined by means of Casagrande apparatus, and the soil passing through 425 micron is to be used for conducting the test in the laboratory, and this is Casagrande apparatus, and normally the procedure is known for everybody, and when a groove is cut and blows given, if I count the number of blows required to close the groove. And liquid limit is the water content corresponding to the number of blows equal to 25. When the number of blows equal to exactly 25 for closing the groove, the water content in that soil is called the liquid limit. Liquid limit. And the liquid limit in the laboratory can be found by means of plotting a graph. We can look at last diagram. It's a plot of water content and number of blows. Number of blows on log scale x-axis, water content on y-axis. So in the laboratory, what we do is we go for different trials of water content for the soil, and we conduct a test. And it may, for closing the groove, it may be different number of blows, and based on the number of blows and its corresponding water content, plot the graph. And finally, corresponding to 25 number of blows, the water content is called the liquid limit. Liquid limit is the water content corresponding to 25 number of blows. You can look at a diagram. 25 at 25 draw the ordinate vertical line so that it meets the line at a particular point. From there draw the horizontal curve and it meets the y-axis, and at that point the water content is called the liquid limit. So liquid limit is the water content corresponding to the 25 number of blows to close the groove when tamped. Okay, and this is the line between the water content and number of blows. Look at the left figure. There are two different water contents considered, W1 and W2. So water content W1 corresponding to the number of blows N1. When the number of blows are N1, the soil water content is W1. Similarly, when the number of blows required for soil to close the groove is N2, the corresponding water content is W2. So this is a simple relation, W1 associated with N1, W2 associated with N2, and by finding the slope, that slope is called the flow index, IF. IF is the flow index. IF is the flow index, which is the slope of this graph. If you call this as theta, so tan theta will be equal to W2 minus W1, this ordinate divided by horizontal ordinate in terms of log scale. So you can look at tan theta equal to W1 minus W2 by N1 N2 minus N1. But N2 minus N1 is always on for the log scale. So it's an important curve, and this flow index curve will give some idea of the variation of the shear strength. And normally, when the soil is in a liquid state and it lost the entire shear strength of soil, and shear strength for of soil, any shear strength of any type of soil, when it is at a liquid state, it is always 27 kilonewton per square meter. When the soil is in plastic state or semi-solid state, shear strength will be more. But once the soil is in a liquid state, all properties will lost, and whatever may be the type of soil, the soil is having a maximum shear strength of only 27 Newton per meter square. And you can also look at this. These are the different types of graphs from the different soils A, B, and C. For the same water content, A, B, and C are the different flow index curves. So here, curve A is having more slope than B and than C. Out of these, C is having more shear strength than FB. Figure B, and it is more than B. A. So here we can understood that slope of A line is more. What is slope? Slope is called the flow index. Flow index is more for A and less for C. And whereas shear strength of soil is more for C curve and less for A. That means shear strength is always inversely proportional to the flow index. Shear strength is always proportional to the flow index. Then another one is plastic limit. Already I told you basic definition. It is the water content at which soil tends to pass from plastic state to the semi-solid state. So here we need to find out various mode how to calculate the plastic limit. So in case of liquid limit, Casagrande apparatus is being used, and water content corresponding to the 25 number of blows is called the liquid limit. In case of plastic limit, we always test the plasticity of the soil. So when the soil is taken and it is rolled to a thread of 3 mm diameter without cribbling, then the corresponding water content is called the plastic limit. And normally what we do is, by taking some soil, we try to make a thread, and when the thread is almost 3 millimeters and there is no cribbling, then the water content corresponding to that is called the plastic limit. Next, one more is shrinkage limit. So in case of shrinkage limit, and it's a very peculiar one. At the shrinkage limit, the entire soil is in completely saturated condition. If a small quantity of water reduced, then shrinkage limit, it is not completely or perfectly saturated soil. So shrinkage limit is the water content below which any reduction of water content will not change the volume of the soil. Volume of the soil is always constant. Now let us see how to calculate the shrinkage limit. So normally, before going for that, let us have a look at it. At shrinkage limit, shrinkage ceases. Shrinkage ceases means reduction of the volume is not going to change. Reduction of the volume of the soil is not going to change. So shrinkage ceases. There is no change in volume. And in case of expansive soils are having more liquid limit less plastic limit, less shrinkage limit, more volumetric shrinkage. Whereas if lime is adding to the swelling soils, any swelling soil, liquid limit increases, plastic limit increases, shrinkage limit also increases, whereas swelling potential decreases. When originally the soil is having the swelling properties, and because of the addition of lime, the swelling is going to reduce. So now look at these diagrams. It is mainly for the analysis of the um, shear shrinkage limit. Shrinkage limit. Originally, the soil pat at initial stage. You can look at the first diagram. First diagram. So this is called the initial stage of water content. So volume VI, that means initial volume of the soil. WI, it is also initial volume of the soil. And once the initial volume of the soil, once it some amount of water reduced, then it will be changed to shrinkage limit. At the shrinkage limit, let us call Vm is the volume of the mass, Wm is the volume of the mass. And after shrinkage limit, assume that the soil is completely dry in condition. Okay, from shrinkage limit to any type of state of the soil below it, there is no change in volume. You can look at the second diagram and third diagram are both one and the same. There is no volume change. Volume of the soil in the diagram 2 at shrinkage limit is same as volume of the soil in the third diagram at dry condition. So originally there is a reduction in volume. That reduction in volume is Vi minus Vm. Vi is total initial volume. Vm means volume of the moisture, fully moistured soil, Vm. So we can look at the top, there is a reduction of Vi minus Vm. So volume reduction is Vi minus Vm. What is the total reduction? Total reduction is multiplied by gamma W. Because from here, from first diagram to second diagram, the change is only some amount of water is lost. Some amount of water is lost. So what is the weight of water lost? Weight of water lost will be difference of the volume multiplied by the density of the soil. So this is the base concept for the derivation of the shrinkage limit. You can observe here Vi minus Vm multiplied by gamma W is the mass of the water reduced. Mass of the water reduced. Now let us see the various terminology. Loss of water from initial stage to shrinkage limit. What is the loss of water? Vi minus Vm is the reduction in volume. Reduction in volume of water multiplied by gamma W, so that you will get reduction in loss of water during the reduction. And similarly, weight of water at shrinkage limit. What is the weight of water at shrinkage limit? This is the shrinkage limit. In this shrinkage limit, what is the weight of water contained in it? What is the weight of water contained in it? Weight of water contained in it will be total water weight, total weight of water. You can look at here. Total weight of water means Wi minus Wd. Total weight of water means Wi minus Wd minus the difference of it. What is the difference of it? You can look at here. Wi minus Wd means Wi minus Wd means total initial water content. You compare with the diagram 2, diagram 1 and 3, and difference of these two will be the initial water content. And what is the water content in the second one? Water content in the second one is water corresponding to the shrinkage limit. So that will be obtained by deducting volume lost Vi minus Vm multiplied by gamma W. So you can look at here Vi minus Vm into gamma W. So this is first term is the initial weight of water, and second term is volume of water lost, so that this is the volume of water at the shrinkage limit. So Wi minus Wd minus Vi minus Vm into gamma W by Wd is the shrinkage limit of the water. And here you can look at Wi minus Wd by Wd is nothing but the initial water content. So initial water content minus some small equation will be the shrinkage limit of the soil. Or otherwise, we can also obtain in another mode. We can also obtain in another mode by comparing these last two diagrams. What is the water available at the shrinkage limit? Water available at shrinkage limit is difference of 3 and 2. Difference of 2 and 3. So when the weight of the soil in figure 2 minus weight of soil in figure 1 will give you water. Will give you water corresponding to the shrinkage limit. So that is another one. Vd minus Vs into gamma D, gamma W, W by Wd. So Vd by Wd is nothing but, you can look Vd by Wd, it means Wd by Vd, which is nothing but gamma D, and already gamma W available. Then Vs by Wd, and here you will get 1 by G. So Wd means gamma W multiplied by Vs. Vs gets cancelled, and ultimately you will get 1 by G into 100. So shrinkage limit can be obtained by means of expression 1. Shrinkage limit can also be obtained by the second expression, and in this gamma D value can be obtained by means of the known relation. And this W is equal to gamma W by gamma G. You can substitute the value. You can substitute the value gamma W by gamma D. You can see gamma D means G gamma W by 1 plus E, and so that you will get 1 plus E by G minus 1 by E. And if you cancel certain things, ultimately shrinkage limit is equal to D by G. So there are three different formulas for computing the numerical problems. One is the first one. Second one is Vd minus Vs by Wd into gamma W. Third one is E by G. Next, shrinkage ratio. So how much shrinkage occurs in the form of a ratio when water content varies from initial to final. So normally Wi means initial water content in the soil. Ws means water content at the shrinkage limit. So when the water in the soil changes from initial stage to the shrinkage stage, the variation of the volume is called the shrinkage ratio. So that's why the shrinkage ratio means Vi minus Vd by Vd into 100, and this shrinkage occurs over a water content distance of Wi minus Ws. This is the equation. You have to remember the equation in somehow. Shrinkage ratio means it is volume reduction of the volume of the soil when the water content changes from Wi to Ws. And the change in water content is given by small formula Wi minus Ws equal to Vi minus Vd into gamma W by Wd. So this is obtained from the previous diagram. From the previous diagram. So initial weight minus sinkage limit of water content will give you Vi minus Vd by Wd into gamma W. And by substituting this W1 minus Ws in sinkage limit, you can look at Vi minus Vd will get cancelled, and finally Sr will be equal to Wd by Vd into gamma W. So after substitution of Wi minus Ws in the original equation, you will get Sr equal to Wd by Vd into gamma W. So what is Wd by Vd? Again Wd by Vd is nothing but, what is that? Wd by Vd, it is nothing but dry density. Wd by Vd is nothing but dry density. So Sr is equal to dry density divided by gamma W. What is the gamma D by gamma W? Gamma S by gamma W means it is specific gravity. But gamma D by gamma W means it is mass specific gravity of the soil. So shrinkage ratio can be defined as mass specific gravity of the dry soil. Mass specific gravity of the dry soil. Similarly, another definition, volumetric shrinkage or volume shrinkage. Volumetric shrinkage, how much volume shrinkage from initial stage to dry state, in the initial state to dry state. So Vi minus Vd by Vd into 100, and you know from this equation, Sr equation also, it contains Vi minus Vd by Vd into 100, and basing on that Vs equal to Sr into Wi minus Ws. So that means shrinkage, volumetric shrinkage or volume change will be equal to Sr multiplied by difference of the water content. You need to remember some of the formulas. Degree of shrinkage. So degree of shrinkage means it can be shrink from any water level to any other level. When water content is W1, the volume is V1. When the water content is W2, the volume is V2. So instead of W parameters, you can also use volume parameters V1 minus V2 by V1 into 100. It is the degree of shrinkage, and degree of shrinkage is for any soil condition. Linear shrinkage. Sometimes the shrinkage may occur only in one direction, and according to the particular direction, that will be taken as reference and calculating the linear shrinkage. Linear shrinkage means it is a shrinkage predominant in only one particular direction, and shrinkage will be measured according to the particular direction only. Then plasticity index. There are two indexes, plasticity index and also consistency index. So this plasticity index is normally used to represent the water content, the natural water content available in the soil between the plastic limit and liquid limit. That is the main objective and purpose of understanding the plastic index concept. And it is defined as plastic index. It is defined as the difference between the liquid limit and plastic limit. It's a very simple thing, and you need not worry about much. Plasticity will be the difference of liquid limit and also the plastic limit. And plasticity index for sands is 0. For sands, there is no cohesion and no plasticity property of the soil, and hence plasticity for sands is always 0, and these properties are to be evaluated only for the fine grained soils, particularly the clay soils. And depending on the plastic index of the soil, we can call different names for the plasticity: non-plastic, slight plastic, low plastic, medium plastic, high plastic, very high plastic in nature. And sometimes the questions may be some numerical values are given for liquid limit and plastic limit, and the final answer may be the type of soil, the type of plastic soil is medium, high, slight, very low, etc. May be the options. And increasing order of plasticity index. Normally, plasticity index will be more for the more fine materials. And normally, soil is composed of several minerals, out of which three important minerals are montmorillonite, kaolinite, and also illite. And montmorillonite is having very fine particles and which are susceptible to high shrinkage and swelling characteristics, and it is more plastic in nature, and plasticity increases for montmorillonous mineral present in the soil, and the order of increasing order of plasticity will be plasticity index is more for the montmorillonite and less for kaolinite and still less for the illite material. Then these are the two things: liquidity index and also consistency index. This liquidity index or water plasticity ratio is used for for analyzing the natural water content in between liquid limit and also plastic limit. The position of the water content to be incorporated in between liquid limit and plastic limit. We are going to scale out something such that water content is represented between plastic limit and also the liquid limit. It is defined as IL equal to the W minus WP by IP. So that means the difference of nature, it is the ratio of the difference of the natural water content to the plastic limit divided by plasticity index, IP plasticity index. And plasticity index means, WL minus WP, WL minus WP. So accordingly, the IL can be 0 when water content is at plastic limit, and IL value equal to 1 when water content is at the liquid limit. And similarly, the IL value can be more than 1 and also less than 1. If the value is more than 1, the soil is completely in liquid state condition. When the soil is less than 0, soil is in solid state. So mainly this liquidity index is concept is used to scaling the natural water content in between the liquid limit and also the plastic limit. Just try to remember the basic equation. Basing on that, you can answer any of the questions. Consistency index or relative consistency. This consistency index is mainly used for knowing the shear strength of the soil, how much the soil is consistent and what are the relative properties, etc. And it is also scaled in between plastic limit and also the liquid limit. So when the soil is exactly at the liquid limit, the value becomes 0, and when the soil is at plastic state, the value is equal to 1. and sum of the consistency index and the liquidity index will become 0. So liquidity index will start from plastic limit, whereas consistency index will start from liquid limit. So that is the difference, and sum of these two will be exactly equal to 1. And classification of consistency. It is generally varies 1, that is between liquid limit and also the plastic limit. Depending upon the values of the consistency index and liquidity index, the soils are classified as very stiff soils, medium soils, soft soils, and also very soft soils. So appropriate idea of the range of the consistency index, liquidity index are more important. Similarly, shrinkage index, like plasticity index, it is a shrinkage index. It is the difference between the plastic limit and shrinkage limit. Toughness index. Toughness index is the ratio of plasticity index to flow index. Plasticity index means difference of liquid limit and plastic limit. Flow index means it is the slope of the liquid limit line. Slope of the liquid limit line. And when IT is more, toughness is more shear strength. When IT is more, shear strength of the soil will be more. And accordingly, when IF is more, IF flow index is more, shear strength is less. That means shear strength is always inversely proportional to the flow index. Then thixotropic material. There are some certain types of soils which lost their strength and also gains their strength without any change in volume of water. Without changing the volume of water, some of the soils will lost their strength and automatically regain their strength. Such type of soils are called the thixotropic soils. You can look at here. The soil is having shear strength property tau versus time. As the time goes on increasing, the property drops, the shear strength drops from this level to minimum. The shear strength of the soil is reducing suddenly, and over a period of time, automatically the strength of the soil increases gradually without any extra effort. And again the soil will lost its property and is again regain its original property. So that means the soil which possesses losing the strength and gaining the strength automatically without addition of any quantity of water are called the thixotrophic materials. Then activity of the soil. So normally the term is involved with the fine grained soils. For fine grained soils, the surface area is more, and when the surface area is more, the reaction of the chemicals, if at all present, will also be more, and particularly all the clay soils will be obtained from the chemical weathering, and it possessing some chemical properties, and because of possessing chemical properties, activity of the soil will be different for different soils. So whether the soil is more reactive or not will be determined by the activity of the soil, and it is the ratio of plasticity index divided by clay fraction finer than 2 microns. A is equal to IP. IP means liquid limit minus plastic limit. C means percentage of the finer fraction less than 2 microns. If the two values are given, automatically you can find out the activity of the soil, and activity of the soil is depending on the numerical value of the activity value. It is inactive soil if the value is less than 0.25, and normal soil if the activity ranges from 0.75 to 1.25, and more active soil if the value of the activity is more than 1.25. So you can look at in the form of the diagrams IP versus water content. As the water content increases, IP value also increases here, and there are three different types of curves. In the first range, x-axis and curve A equal to 0.75, whatever the soils that falls under this area are inactive, and soils that fall between A equal to 0.75 to 1.25, these are called the normal soils, and above that the soils are very highly active. And with respect to the various minerals present in the soil, montmorillonite, illite and kyalanite. Kyalanite is low reactive material than illite, and montmorillonite is more active material, which is having A equal to more than 0.9. Then sensitivity, last point, sensitivity. Sensitivity of the soil is defined as unconfined compressive strength of the undisturbed soil divided by unconfined compressive strength of the remolded soil. So that is called the sensitivity. Sometimes a small question may be asked based on this particular simple formula by giving the unconfined compressive strength of undisturbed soil and also the remolded soil. And depending upon the range of sensitivity values, the soil is classified as honeycomb, stable, flocculent, unstable, etc. And we can also call it as less sensitive, sensitive soil, extra sensitive, quick sensitive, like that. So you just understood the meaning of it. Compressive strength of unconfined, undisturbed soil sample divided by unconfined compressive strength of remolded soil sample. So with this, the basic definitions of the properties of the soils is completed. In the next class tomorrow, we will take up the numerical examples in detail. In detail. So today I will send the material. Actually, yesterday I have not sent the material to JNTU officials. Today I will send immediately the material to officials. They will keep in website, and you can download the same material and read all the contents, and be ready for the solving numerical problems tomorrow. Thank you very much.